Hello. So for today, I'm going to be doing question 2 from chapters 25 to 26. And today is going to be talking about mainly discussing EMF force, then how current and voltage and resistance all play together. So the main things main formulas we're going to be using for this be that voltage from A to B is equal to EMF, so E or epsilon will be our EMF. So EMF minus current times little r, and little r will be our internal resistance. Now EMF is pretty much, as the charge is moving, it's going to, through like a circuit and a resistor, it's going to lose potential energy crossing through the resistor. So it needs something to kind of push it and keep it going back uphill. Just like how the potential energy wants to slowly go to a baseline, something needs to keep pushing it so that the source is going through. And pretty much electromotive force, which is EMF, is that source. It's like a pump. It's kind of pushing the current all the way through. Although it's not exactly a force, it is the energy per charge that's being put in through volts. So we'll say it's energy per charge in volts. Now, every single one of these, every source that is giving off an EMF is going to have an internal resistance. So this is pretty much just saying that no battery is going to have a constant voltage to it. It's not going to be forever. It's not going to be a constant current of source. So if we have a battery, it's connecting through a resistor. When we start thinking about EMF, we have to think about it as, when we diagram it out and we have our battery right here, we have to look at it as the battery actually has a resistor right there. So it has its internal resistance as it's moving through. You know, in old batteries, so they're pretty much, as a battery either gets old or it gets cold, any change of it will change its internal resistance and can make the current lessen as it goes through. So it makes us know that no battery is going to have a constant current source. Pretty much bigger external R or internal R, pretty much just means it's going to be less current throughout. So I'll pretty much just sum up that EMF is not a force, but it's the energy per charge. And we see that right there. The actual force gives us our voltage here. Let's subtract it by the current times the internal resistance. And then as well, we're going to be using how we can figure out current is equal to the EMF over divided by the resistance plus the internal resistance, and this can give us the current of the whole circuit. Okay, so let's start off with part A. So part A, it's pretty much saying that a battery, so we have a battery here, is with an EMF of 9 volts. It's a battery and has an internal resistance of 1.10 ohms. And it's in a complete circuit, so let's draw this out. A complete circuit with a resistor, resistance of 15.3 ohms. So we'll have a resistor here. Connected back. This is 15.3 ohms. Now we have to find the current of the circuit. So we're pretty much given every single value that we need to be able to find out the current using this previous formula that we have right here. So we'll just know that I is then equal to, we'll just plug everything in. Since our voltage here is an EMF, we'll then put it in, so it'll be 9 volts all over our big resistance of 15.3 ohms plus our internal resistance of 1.10 ohms. So let's add that. Let's put that all together. So it will be 9 divided by 15.3 plus 1.10. And then that's going to give us a current of 0.54, round that over to 9, 0.549 amps. All right, so let's move on to part B. Part B is to then find the potential difference across the resistor. So if we have to find the potential difference across the resistor, we'll pretty much just use our currents that we figured out here and then apply it into this formula right here that we have right here, which pretty much just shows our voltage, which is our potential difference from A to B. So potential difference from A to B is then going to be equal to our EMF, which is 9 volts, minus our current, which is going to be 0.549 amps, times our resistance, which is our terms 1.10 ohms. And now a good thing to notice as well is that when we're seeing this voltage, this potential difference, we can honestly see it as two different voltages being subtracted by each other. That's why it's from A to B. We have our starting voltage that pretty much is our starting EMF force, pushes through, and then to come back through it, it's pretty much the current multiplied by our resistance, which is another voltage right here, because it relates to how V is equal to IR. And since this little r is still resistance, it's still going to be a current times a resistance that's giving you a voltage. So it's a way to see how the potential difference of V of A of B is simply just the voltage given minus the voltage that is then going back in, and that's your potential. There's a way to then look at this. Well, let's solve this right here. We have 9 volts. It's going to be 9 minus, we have right here, focusing, but 9 minus 0.549 times 1.10, and that's going to then give us 8.396. So we'll round that over to 8.4 volts. And there we go. That's going to be our answer for part B. Let's go down to part C. So part C. Pretty much you then have to find the potential difference across the battery terminals. So what we did first is that we pretty much just did through the resistor. We actually flip-flopped them. The first one was through the resistor. So I'm going to do pretty much part B. What we did first was part C. Part B is just going to be pretty much V is equal to IR, where we have our voltage is just equal to potential difference of voltage equal to our resistance of 0.549. Our resistance, our current amps multiplied by our 15.3 ohm resistance. And that's going to give us 0.549 times 15.3. Relatively the same answer, just off by a couple decimals, because there is a slight difference to them. So it will be also 8.4 volts. So what the first thing was asking, part B was asking find the potential resistance across the resistor, across this resistor right here that we have. So it's pretty much the voltage difference across this resistor. So as the current goes through this resistor, what is our voltage? And then there's also voltage on the battery, which is pretty much as the current goes through the battery, what is the voltage coming through here? We pretty much just flip these. So I'll just erase these and say this is part C and part B. This is why it's also good to name that we are looking for voltage of the resistor is equal to that. This voltage from A to B is pretty much voltage of the battery. There we are. So let's move on to part D. So part D. So now we have a new scenario here when an automobile battery with an EMF of 12.6 volts. So pretty much we have an EMF right here. We know we have the battery, 12.6 volts. It's connected to a resistor of resistance 25 volts or 25 ohms. So a resistor, it's coming back. 25 ohms. And we know that our current I is equal to, it's saying that our current is 0.480 amps. So we have to find the potential difference across the resistor. So pretty much, what is the potential difference across this resistor right here? So that's just real simple. Part D, we just know that voltage of the resistor is equal to, obviously V is equal to I times R. So it's going to be 0.480 amps times 25 ohms. 0.480 times 25, it's going to give us 12 right there. And that one gives exactly 12 volts. So across the resistor, it's going to be 12 volts. That's going to be our answer for part D. So then part E is then going to be find the internal resistance of the battery. So here, we have to figure out what is our internal resistance. So what we're going to be using is we can use either or of one of these equations. It really just depends how you want it because they both have internal resistance in it. I'm going to use this first one right here, where I'm going to say voltage from A to B is equal to E, or our electromotive force minus resistance times our internal resistance, or our current times our internal resistance. So we're going to first essentially subtract this to the other side. Also, A to B is a minus our electromotive force. Then we divide by negative current. So essentially it's going to say that our internal resistance is equal to the potential difference minus electromotive force, actually plus electromotive force, because that's divided by I. Yeah. What should I flip those around? Yes. See how my answer goes over a current. Which is pretty much going to equal. I might just switch this to a different one, but our potential difference could be 12.6 plus 12 all over 0.480. Oops. Sure, it's voltage right here. I have not been showing this part. Oopsies. There we go. There it shows. So let's do this right here. We have 12.6 plus 12 over 0.480. That was not the right answer. I have to flip these around. Let's not use this one. Let's use the other one that we have that are more simple to use. Where we have current is equal to electromotive over R plus little r. Essentially, but then we'll just multiply this on each side. So we'll multiply our R plus R on each side. And then we'll divide by the current. So this will move here. This will move here. So then we're left with big R, little r is equal to electromotive divided by current, subtract R big R minus big R. So it should be little r is equal to electromotive force of the current divided by current minus the big R. So this is going to be 12.6 volts, which is the electromotive. Maybe they should have been flipped around. So that's a resistor divided by current 0.480 plus 25. It's going to get a new number. It's going to be interesting. This should be 1.25. Off here. Let me see here. 12.6 to 0.4880. That's 26 minus 25. So yes, there we go. Minus 25 ohm amp. Yeah. And then that should give you 1.25 ohms. So essentially, we're going to take our second equation that we got, and then we're just going to flip our variables around till we have it where, let me write it more clearly over here, our internal resistance is equal to electromotive force over current subtracted by resistance. So, and then here we have the electromotive force divided by current subtracted by resistance. It should give you 1.25 ohms for the internal resistance, and that should be your answer for part E. All right. To the next ones. Okay, so now we'll be at part F. All right, so new scenario here again. So a AA battery has an EMF of 1.50 volts. For being used for quite a while, one AA battery has a potential difference across the terminal of 1.30 volts. It's connected to a light bulb with a resistance of 20 ohms. So we have a circuit here, a resistance of 20 ohms, which is a light bulb here. And we know that currently our electromotive force right now, I would say that it is 1.5 volts. That's what it should be. But potential difference is turned into 1.30. So it's asking us, we have to find the current. So what's going to be the current for this? Now, we know that if we have V equals I times R, we can just flip it around where current is equal to voltage over resistance. Since we have our main voltage, we have our main resistance, we can just figure out the total current. So total current will be equal to 1.5 divided by 20, which gives 0.07. Wait a minute. Not that voltage. It should be, this is, oh yes, that's right. It is, should be 1.5 volts, but is now 1.3 volts. So our voltage should be equal to 1.3 volts over 20 ohm. So not 1.5, but 1.3, because yeah, it has potential difference, because after quite a while, it is now at 1.3. So 1.3 should be 0.065 amps. That'll be the answer for part F. So then using the same graph, we're going to solve for part G. Part G is answering by the internal resistance of the battery. So this time, because last time we were not given the voltage difference, this time we do have the voltage difference. We know that it's 1.3. So what we can say this time is that when we have voltage difference, our potential difference is equal to our electromotive force minus our current times internal resistance. If we have to figure out the internal resistance of the battery, what we do is pretty much what we did last time, where we do is subtract this to the other side and then divide by the negative current. And that will pretty much give us our potential difference minus electromotive divided by, now when we're dividing by this negative current, this is going to turn this positive, but this is going to turn this negative. So it's going to turn into electromotive force minus the potential difference divided by the current is equal to the resistance, the internal resistance. That's how it should be flipped around. So that is going to be 1.5 volts, which is our original EMF, minus what it currently is, which is the potential difference of 1.3 volts, divided by our current, which we just figured out, which is 0.065 amps. So our internal resistance, once we put all this together, 1.5 minus 1.3 by 0.065 should come out to, we're going to round that over to 3.08. Internal resistance should be 3.08 ohms, and that's for part G right there. So there we are. So now, next scenario, we go to part H. So pretty much the manufacturer of one brand of AAA battery states that the battery EMF is 1.50 volts. Its internal resistance is 0.160 ohms, and the maximum allowed current for a short time is 2 amps. So, find the smallest resistance to which the battery can be connected for short times. So what is the minimum resistance here? So we have a battery. Battery at 1.50 volts. And we know that its internal resistance is also 0.160 ohms. And we have to figure out what is the smallest resistance to which it can be connected. So we have a voltage, and we have an internal resistance, and we have a current as well given to us, and that current is 2.00 amps. So if we solve this with 2.00 amps as our short burst, our maximum current for short time, then what we can use is the formula where current is equal to EMF force, where it's the big resistance plus internal resistance. So this time, we're solving for our outside resistance instead of the internal resistance. So it's going to be pretty similar to how we did it in the previous parts to flip these around. So essentially, how we're going to multiply our resistance plus our internal resistance onto this side, but then divide our internal back over under the E. So then we'll have our big resistance plus our small resistance is equal to electromotive divided by internal, this time subtracted by internal resistance. So resistance is equal to electromotive force divided by current minus internal resistance. I'll write it over here. So R is equal to our electromotive force, which you have here, is 1.5 volts, divided by our current, which is 2.00 amps, minus 0.160 ohms for our internal resistance. So we're just going to plug this all in. 1.5 divided by 2 minus 0.160. And that should give us 0.59 ohms. 0.59 ohms will be the minimum resistance to the current given. And then we have to find, for part I, we have to find the potential difference across the battery terminal when it is connected. So if, let's say, we connected this battery into a circuit, now what is going to be our potential difference from our A to B point, essentially? And so we're pretty much just figuring out our potential difference from A to B, which we use our formula, is equal to electromotive force minus current times internal resistance. Now we already have all of these values right here, so we can already figure this out right now. So V from A to B is equal to our 1.5 volts. Let me fix this up. Minus the current, which is 2 amps, multiplied by internal resistance of 0.160 ohms. 0.160. So we're just going to plug this all in. 1.5 minus 2 times 0.160. And that's going to give us a voltage difference of 1.18. Voltage difference is 1.18 volts. That will cover all the parts for electromotive force, internal resistance, and thank you very much.